All right, so we're going to dive into more motion terms to give us a better way to describe motion using words. And then we're going to look at motion in graphs, and then finally we're going to move into more of the equation stuff. So this goes along with page 2 in your packet. So we just finished talking about displacement and distance and understanding that there's these vectors and these scalars. So we're going to focus more heavily on the vector form. The reason we want to focus on vectors, it's more information. It allows us to put more stuff into our equation and get better answers out. So the first thing we're going to talk about is position. So if you have a location, you have a position. And we're only doing one dimension at the moment, so we're just going to use X at any given time, or maybe if we're only doing one dimension in the vertical, we'll use Y. All right. Displacement, which we talked about, describes a change in that position. So we use that delta X to describe final minus initial, the change in that X. Now our new term, velocity. Velocity is a lot like speed. The difference here is velocity is a vector, velocity vector. Okay, so this uses displacement over time, whereas speed is your distance over time. So again, we're going to be focusing on vectors. So we are going to be using the velocity, which describes how fast the rate of change in your position. So how fast are you changing your position? That is what velocity describes. And so you'll notice that displacement and velocity seem similar. They describe changes in position. One of them just describes the change. The other one tells me how fast did the change occur. Right? And then for the next one after velocity, acceleration tells me, well, how fast are you changing your velocity? What is the rate of change in velocity? And acceleration is A. Now we keep going. This goes on for a ways. Jerk describes a rate of change of acceleration. So you're going to start to see a pattern, rate of change, rate of change, rate of change. Snap describes a rate of change of jerk. Now, let's see if you can figure it out. What would the next two be? We have snap. If you shout it at the screen, crackle and pop, you got it. Snap, crackle, pop. But lucky for us, here in traditional physics, there are no jerks, so we will be having no rate of change in acceleration, meaning our accelerations are constant. We do this to make our lives a little easier and so that we don't have to involve calculus. So that's going to be kind of the nice thing for us, is these things exist down here, just know that. But we are going to kind of simplify our world a little bit to a situation where there's no jerks. How nice is that? All right, so let's define one more term. So we are going to define something called average velocity. It's really hard to find an instantaneous velocity because it's requiring a change in your position. And if your change in your position is 0 because you're at an instant, it's really hard to kind of find that. So we tend to talk about average more. So average velocity is defined, and that's what those 3 equal signs mean, that's a definition, as the displacement divided by the time. And this equation always works. Now some of you are thinking in your head, average? I'm pretty sure average is like you add them all up and divide. And so you're like, well, why couldn't I just say how fast are you going at the start? How fast are you going at the end? Add them up and divide by 2. And this is a conditional equation. This one only works if acceleration is constant, meaning it only works if there's no jerks. Well, lucky for us. This is going to hold true as well. But I really want to kind of stress here, though, that this works always. This only works in certain situations, which we kind of have focused this class on. So just keep that in the back of your head. So what we're going to do next in the next video is we're actually going to try some problems trying to get these words into some equations and figure this stuff out.